What types of problems can you do using integration by parts? Well, most integration by parts problems fall into three basic categories. You have type 1 problems, and type 1 problems involve functions like sine x or e to the x that would be easy to integrate if they were alone, but they're multiplied by some factor like x or x squared or some polynomial. And you can use integration by parts to get rid of these factors. You also have type 2 problems, and type 2 problems involve natural logs and inverse trig functions. And you can use integration by parts on these to transform functions like this or this into functions that are easier to integrate. You have type 3 problems like these, where you can use integration by parts to get the original integral to reappear on the other side of the equation, but with a different coefficient. And you can sometimes solve a problem like that, or at least simplify a problem like that. You have type 4 problems that aren't easy to classify and don't fall into any of those three categories. And problems like these require making some clever choices. Now, what is integration by parts? Integration by parts is basically this formula over here that tells you you can transform an integral like this into an integral like this. And the new integral may be easier to integrate than the original. And integrating it involves choosing a u and a dv so that your integral is of this form. And I'll demonstrate that with the type 1 problem. I'm going to let u be x, and u has to be either part of the integrand or the entire integrand. So whatever is left over, including the dx, becomes dv. And if you chose dv first, whatever parts of the integrand that were left over would be u. So u is equal to x, and dv is equal to sine x dx. So if you go back and look at the formula again, the formula says that you need a v and you need a du. Well, you can get the v just by integrating this, and you can get the du by taking the differential of this. The differential of a function of x is just equal to the derivative of the function with respect to x times dx. And the derivative of x with respect to x is just 1. So that's 1 times dx. And to get v, you just integrate both sides of this, and you get v is equal to the integral of sine x dx, and that's equal to minus cosine x. And when you integrate this to get v, you don't need to add a constant of integration. So the formula tells us that we need u times v, which would be this times this, minus the integral of v du. So that would be minus the integral of this times this. And I favor laying out the u's and the v's according to this pattern, like this, and across like this, because this corresponds to the tabular method of doing integration by parts. So the original integral is equal to u times v, which is this times this. So I'll put the minus sign first. So you have minus x times cosine x. Minus the integral of v du, and v is equal to minus cosine x. So that's equal to minus x times cosine x. And I'll take this minus sign and I'll bring it outside the integral, so I'll have plus the integral of cosine x. So when you differentiated the x, you just got 1. So when you set up the integral, you're only left with an integral of cosine x. So basically you've gotten rid of this x over here. So this is equal to minus x times cosine x. And the integral of cosine x is just sine x. Plus a constant. Now if this problem were a little different, for example, if it were x squared over here, you could just choose the u equal to x squared and apply integration by parts twice. So you'd end up knocking the x squared down to a constant, and you'd just be left with the integral of sine x. And if it were x cubed over there, you would just apply integration by parts 3 times. And here's a type 2 problem. There's only one term in the integrand, so I'll just choose this to be u, and what's left over will be dv. So u is equal to ln of x, and dv is just equal to dx. So du is the derivative of ln of x, which is just 1 over x, times dx. And dv is just the integral of dx. So v is equal to the integral of dx. So v is just equal to x. So you need this times this minus the integral of this times this. So the original integral over here becomes u times v, which is just x times ln of x. Minus the integral of v du, and v is just x. And du is 1 over x dx. Now the nice thing about this is these x's cancel. So this is going to be equal to x times ln of x minus the integral of dx. So this is going to be equal to x times ln of x, and minus the integral of dx is just equal to x plus a constant. And you can easily differentiate this to see that you get this back over here. You can use the product rule on this. Now here's another type 2 problem. This looks like a type 1 problem, but if you were to try to do it like a type 1 problem and choose u equal to x squared, so that dv would be equal to this, you have u is equal to x squared, and dv is equal to ln of x dx. Then du is just going to be equal to 2x dx by the power rule. And v is going to be equal to the integral of natural log of x dx. But we just did the integral of natural log of x, and this is the result. So v is equal to x times ln of x minus x. So when you differentiate the du, you get something simpler. There should be an x here. When you differentiate this, you get something simpler. But when you integrate this, you get something more complicated. And you get this extra factor of x. And that should be a natural log of x. But when you do a type 1 problem and you differentiate the x, you knock it down by 1 degree. But when you integrate this part, you get something similar and you don't get any extra powers of x. So what I'll do is I'll let u equal this ln of x, and then dv will be whatever's left over, x squared times dx. So I have u is equal to ln of x, and dv is equal to x squared dx. So du is equal to the derivative of natural log of x, which is just 1 over x times dx. And v is equal to the integral of x squared dx, and you can do that by the power rule, and you just get x cubed over 3. So you need u times v minus the integral of v du. So the original integral over here is going to become this times this, so you'll have x cubed over 3 times ln of x minus the integral of v du, which is minus the integral of this x cubed over 3 times du, which is 1 over x dx. So the nice thing about this integral is that this x cancels with a power of x over here. And I'll write this as 1/3, since dividing by 3 is the same thing as multiplying by the reciprocal. 1/3 x cubed times ln of x. And I'll take the 3 down here outside of this integral, so I'll have a minus 1/3 times the integral of x squared dx. And that's equal to 1/3 x cubed times ln of x minus 1/3, and you can just do this by the power rule, and you get x cubed over 3 again, plus an integration constant. And I'll just simplify this a little bit. You have 1/3 x cubed ln of x, and I'll just multiply these two 3's together to get 9, so I'll have minus 1/9 x cubed plus c. Now if you were to go back for a minute and look at this original choice of u and dv, it turns out that this can actually be done like a type 3 problem, because when you calculate the integral, you'll have v times du, so you have this factor times this factor over here, which will give you x times x, which is x squared times natural log of x, so you get back this factor over here. But the integral in this case will have a minus 2 in front of it, which allows you to bring it over to the other side and combine it with the original integral. So this can also be done as a type 3 problem, but this method is easier.